Okay. First of all, congratulations, Bob, on your birthday and for everything that you've done for this community. Thank you, Brian, for the invitation, and thank you, NIST, for hosting us, and Jim Klang as well. So today I just want to talk about the influence that Bob and GSAS has had on my career. We've never had the opportunity to work together, but I'll show you that actually I was sort of following you in Los Alamos, so you'll see in a minute. So this is a picture of Bob with one of my former PhD students, Rietveld. And I don't know if you remember this picture. This was at the Pittsburgh Diffraction conference. But Rietveld was really sort of starstruck when she saw that Bob von Dreele was there, and so she insisted on this picture. And so I texted her this weekend. I was like, "Do you remember that picture you took with Bob von Dreele?" And she immediately texted it to me. She said it was one of her favorite moments. She actually also won the poster award at the Pittsburgh meeting, so she was very happy. So this is what I mean by following in your footsteps. 2003 was my first acquaintance with neutrons, and in fact with crystallography. Even though I had studied a little bit in my undergraduate days, I didn't really understand so much. Peter alluded to how tough crystallography is, and so I get there as what's called a post-baccalaureate intern at the Lujan Center, which is here, the Pepto-Bismol colored building. I don't know how many of you have been to Lujan Center. I've seen many Lujan Center people here. And this was the experimental hall. This ER1, ER2, and this is a picture inside. And I was hired to work with Thomas Proffen and Anna Jovet. I don't know if they're online. If they are, hello, at the Lance. So, and it was a lot of fun. There's Anna, and there's Thomas. Anna was trying to convince me about crystals, and Thomas was trying to convince me there's no such thing as a crystal, like the PDF method, so I was very confused. But I was lucky to learn first with GSAS, and I was also lucky that the GUI was also out there. And so I first learned how to solve structures of metal oxides, and in fact that was sort of when I started falling in love with magnetism and transition metal oxides. And I wasn't yet a PhD student. I was deciding whether I wanted to do a PhD or not. I wasn't too sure. So I was there for a whole year. And I was then later convinced, I'll talk about that later. But I think it was difficult to learn crystallography. And then on top of that, I had to learn magnetism and crystallography together. And so Anna had told me there's this thing called full prof, it's really great, and you get to use irreducible representations, etc., to deal with magnetic structures, but you're dealing with time of flight spallation source neutrons, so you better learn GSAS. And so I worked with also Angus Lawson, who was there. And by the way, Anna took over your office, I think, in 2003 when she started there. And so I learned about black-red symmetry and magnetic space groups. And even though EXP GUI was really nice, actually you had to learn EXP edit and go in there and change all the symmetry to do the primed operations and so on. So then I started really learning EXP edit, and actually it's pretty smooth once you get in there. And you start just clicking, right, and getting to refinement flags and so on. And this was the very first paper I've ever written. It was published in 2005 with Thomas and Anna and Jim Ryan, who's here. And it was on the mixed valence manganites. And so these are materials that have charge order, spin order, and also orbital order. And this is data, I think, from NPDF and HIPD, which are the two diffractometers that I mostly worked on. And so I really got hooked on crystallography and trying to understand how structure affects properties in materials. And Al Hurd, who I called up this weekend, told me at the time, you need to go to Santa Barbara and work for this guy named Tony Cheatham. And that was how I got to Santa Barbara and started my career there, really on neutrons and crystallography. Continued it over here at NIST when I was a postdoc at the NCNR. So I like history of crystallography, and I like to dig into the past, all the way to, you know, Kepler and his close packing to describe hexagonal symmetry. And so I started looking into powder diffraction and thinking about how it was done before, and I was really surprised to learn how everything was peak by peak before 1967, and how could you deconvolute what was the area underneath the peaks, and really how Hugo Rietveld had revolutionized this area. And also Pauli, and I look at the dates in Labai in the 1980s, thinking about what was going on in the 80s as well with the explosion of the high T cuprates and so on, and how important, you know, these methods were in the end, right? Neutron scattering, but also doing Rietveld analysis and so on of these materials. And I was able to find this, which is Alan Hewitt's History of the ILM. And it says here that certainly there were huge changes in powder diffraction for small changes in the crystal structures. And with my early experience in computing, I tried to extract that information. And so he says, he remarked that there was some chap in the Netherlands who had been working on just that problem. It turned out to be Hugo Rietveld, the Dutch Australian who worked with Terry Sabina and Lucas Heitz. And what was interesting, I saw this, that later that code was taken by Sir Brian Fender, right? And his students, Tony Cheatham and Bob von Dreele at Oxford. And so it became the base of the subsequent refinement programs. And so I thought that was very interesting to think about sort of the nucleus of GSAS when it was happening. So popularizing the Rietveld method, even though Rietveld had found it in the late 60s, you know, you start seeing in the 70s with Tony's work, CNR Rao, looking, for example, at transition metal oxides like niobium oxide having its metal insulator transition. We have dimerization of niobium. I later on, when I was a graduate student, I came back to Los Alamos and worked on the technetium analog of this TCO2. And with GSAS, I found what should be the correct neutron scattering length. So not a form factor, but I got the scattering length of Tech99 from looking at a root time type structure like this. And then I think Tony talked about this earlier as well, this 1974 paper looking at how the power of neutrons in being able to distinguish between metal sites like titanium and niobium in here as a way to really get out structure in a way that you couldn't have done with X-rays. So, and then the history, so I was showing that in the early 80s, where you had Labai and Pauli, and then this is a paper, I think, one of the big papers of Bob on Rietveld refinement with spallation neutron source, powder diffraction, and then some other papers, for example, this one here demonstrating the power of time of flight neutrons. And so to conclude this part on sort of the history, without GSAS, I think there's no way at the time, right, to deal with this tricky time of flight spallation source neutron data. And so it's really well timed for looking at very important systems, whether we're talking about cuprates or manganites or many different kinds of metal oxides, functional transition metal oxides. And so, as I was saying, Anna had taught me about full prop, and I learned full prop as well. And it's very good, of course, when you're looking at sources like the ILM with nice constant wavelength peak shapes. But really with GSAS being able to do powders, single crystals, then magnetism with spallation sources, I think is a game changer. And we thank you, Bob, for your seminal contributions in enabling that kind of science, not just in physics, but also chemistry and geology. Nowadays, more modern, I guess, up to date, what I like to give my students to think about are papers like by Brian, like how good is good enough. I wish I had seen this when I was starting out, because I think I kept going and going and going. I became obsessive with these refinements, and also these guidelines how to approach it, and also like not losing sight of powders still being so important. single crystals are beautiful, of course. They give us two-dimensional information, but the real world is powders. A lot of what we have to really work with, right, when we're talking about energy materials or environmental materials, depend on powders. So it's always going to be important to be able to tackle those tough problems with powder diffraction. I think I'm just going to present quickly a little bit about some of the science that I'm doing right now. One of the projects in my group is to use transition metal oxides. We look at chalcogenides, but today I wanted to connect back to my experience with metal oxides, in particular perovskites, let's say, and how we can actually use them to transfer oxygen from the atmosphere into another type of system, for example, using them in closed looping with natural gas combustion, or say thermochemical splitting of water to produce hydrogen. And so they're very interesting ways to think about metal oxides besides the physical properties that we're used to thinking, like magnetism and so on. And so what we've been doing is in situ powder diffraction to study oxygen transfer in these materials using both synchrotron X-rays and spallation source neutrons, and thinking about answering questions like oxygen storage capacity. So these are materials not really for storing oxygen. Oxygen is easy to store. It's more about using these materials instead of oxygen from the atmosphere for particular applications. And there are many metal oxides that are actually very reversible because of the fact that they can support oxygen site defects or vacancies and easily cycle back and forth. So these are some of our papers where we do looping between, say, a perovskite and something related to a perovskite, like a brown millerite type phase. And we cycle them in methane and also in oxygen. I want to say a little bit more about the experiments. My students have been going out to 17 VM, hopefully again soon, to do these experiments. And also to Paugen, now that we're still looking at spallation neutron source, and now at Oak Ridge, of course. And shout out to Ashvia for building that Aegis system out there to be able to do this kind of experiment where you can put your material in different kinds of environments, such as methane, hydrogen, and so on, and do these cycling experiments. What we've been looking at more recently are not perovskites necessarily, but these 1,2,4 type structures where you have a rare earth or lanthanide. Here, these have been looked at also for multiferroid type of applications. But we also saw that they're very interesting for doing oxygen insertion. They actually consist of a hexagonal sublattice with a sort of a pseudo honeycomb sublattice in the transition metal site here. I say pseudo because it's kind of like a corrugated honeycomb. It's not a flat honeycomb. And what these materials are good at is actually, this is just a cartoon image of what happens, is they readily take off oxygen, and due to these Coulombic repulsion interactions, the layers just slip past one another. So it goes from a rhombohedral to a trigonal space group, and we wanted to understand how that happens. It's a fairly complex crystallographic transition when you do that. And my student Rishvi, I decided to put Rishvi in here because she's such a fan of Bob and wanted to take that picture. And this is the sort of the work that she did on these 1,2,4 materials using in situ synchrotron X-rays. And this is an example of cycling at 600 degrees Celsius, where we took air and hydrogen. And we look at certain peaks and just look at how the A site, so I said it has to be rare earth. Actually, it doesn't. You can put an indium, for example, on that site. It just has to charge balance. And then my student Tianyu Li played around instead with the B site and putting in iron and manganese in here, a B site mixing type of material. And so we do then powder diffraction as a function of time. And we follow the oxidation. This is, again, some synchrotron data set. And what's remarkable about these materials is that they start oxygen uptake at about 200 degrees Celsius. So they are very oxygen hungry materials. And what we want to figure out is, can they also reversibly release oxygen at relatively low temperature? So they might be actually even better than, say, perovskites are sort of material, go-to material for many type of applications, right? As far as kinetics and also turning down the temperature. So we can see here that phase transition, which is fairly complex, it's first order because you have phase coexistence here of these material of two different phases. This is the time versus some intensity in Q. So now I plot in Q. My very first plots were in T spacing. I know you don't like that, Brian. So I've reformed over the years.
Bubble support in D space.
Oh, really? I mean, spacing is really good for layered materials and for a lot of other things. But it's nice to have everything sort of normalized instrument to instrument. And so I always tell my students, give it to me in Q. So here's the rhombohedral phase, the reduced phase, also we call it the R phase. And it takes up exactly a half molar equivalent of oxygen and only up to that. And this is neutron data from Paugen. And we're able to fit it okay. This is P3 bar. But you can see it's not okay actually, because if you zoom in here, you have a ton of these satellite reflections in there. And so my student Tianyu was able to do some really nice electron diffraction, looking down, say the 001 zone axis. Here's the reduced phase. And then upon taking up oxygen, you see all these nice little satellite reflections that pop up to make this image here. If you look down different zone axes, as you go from rhombohedral to the trigonal, you change bases, but nevertheless, you still see some nice superlattice reflections here. And so what that superlattice reflections are coming to has to do with a propagation vector that's a charge density wave from the oxygens as they insert into those layers. And so it turns out that using the propagation vector that we were able to get from electrons, we're able to go back to the synchrotron source and fit all those satellite reflections, and also the Paugen data fit those satellite reflections. So if we compare all three particles with each other, electron, X-ray, neutron, in the end, we're pretty sure that we can come to the conclusion that you have sort of a 1/7, 3/7, 0 type of satellite that develops as you uptake oxygen into these materials. And so I just wanted to sort of end there, not get too much into the weeds of this, and acknowledge my students, our funding agencies, NSF, DOE, and NIST, of course, as well. And my collaborators, Peter Zavalli, who many of you know, is my colleague at UMD. He sends his best wishes. He couldn't be here today. He's not feeling well, said, but he sends happy birthday wishes. And so
He has been online.
And he has been online. Okay, great. Yeah, so happy birthday. Thank you, Bob. This is when my student was fanning, over. I think they call it standing. And this is a quote I got from Al Hurd at the Lujan Center, and it says, "No small part of the success of GSAS is the many workshops von Dreele teaches on Rietveld refinement, including teaching Oregon's National Scattering School. His generosity with his time is characteristic of his mentorship of many early career scientists." And definitely it's influenced me, it's influenced my students. Now I get to teach at the, it's called now the Oregon Oak Ridge Neutron X-ray School. I teach that with Roger Pinn, actually the first day. We give lectures on scattering. And I think that's very true. I think, just putting out software, I mean, already we're indebted for everybody who puts out software, but going out and actually teaching our young people and our students how to use it to solve some of these tough problems is especially welcome, and we're very grateful for that. Thank you much.